All right, welcome back to episode 5 of the VRF Tech Talk podcast. It's me, Donald Felice, again joined by Roman Ball. We have a very special guest today, too. Roman, if you want to take over from there.
Yeah, so I found this homeless guy outside looking for food, and but he loves science, so we just kind of let him in, and we've been rolling with the punches ever since. No, this is the lovely Love to HVAC Ty Branaman, actually. So the great thing about working here at Kalos, a lot of the things that we have, is being able to work alongside a lot of special people. And I call him special because he is special. But yeah, no, thanks for being here, Ty. So we literally were in the background doing a bunch of science experiments with oil, which is what we're going to talk about today, actually. And from that part, we kind of just stopped and we said, oh, yeah, why don't we just shoot a podcast while we're also here? Because, again, the great thing about this podcast is that there's no staging, there's no scripts, there's none of that stuff. This is just, technicians talking to technicians about stuff that we want to know about, the problems that we see in the real field, as well as the science behind it and how to understand it. And so that's pretty much all this is about. So, yeah.
Great. Yeah, I mean, I particularly have a lot of unknown questions currently with the state of oil that we're going to get into with the refrigerant change into A2Ls, if there's anything different that we have to worry about when we get to this A2L refrigerant. I mean, oil is oil. Back when I was an automotive mechanic, and like we talk about synthetic blends and conventional oils, and it has this additive, that additive. What else do we have to worry about once we get into this A2L world? So it's an interesting topic.
No, it is a great topic because, again, it's not just the refrigerant. There's more components than just the refrigerant. There's the components inside that deal with the refrigerant and stuff like that, but also a big part of that is oil. So, what do you know about that, Ty? Since you're an expert, no, I'm just kidding.
So I know with your conventional systems, there's a difference, of course, between POE oil and PVE oil. But your conventional POE oils, where you're going from 410A to 454B, is essentially the same oil, the same temperatures, because 454B and 410A are very close together. The key difference is R32, because R32 has a much higher discharge temperature. So it's going to get a lot hotter. And because it's moving more heat, right? I mean, so you're naturally going to have a higher discharge temperature. But to handle that, they have to use an oil that will handle the higher temperature, as well as some components in there. So they do use a different oil so it won't break down at those higher temperatures.
No, it's good. So do you know exactly what oil that is specifically? I'm sure we're staying with PVE because of the things that we talked about today and we'll talk about now, but do you know the exact viscosity?
I don't know those exact numbers. I just know there was a different number involved. Yeah. Okay. And that's why a lot of the VRF systems you see use PVE oil because it can handle that higher temperature.
Yeah,
it's like they designed it for that.
Yeah. No, and so the testing that we did today in the background, which you'll see the video of it later once we edit it and get through all the fun stuff, we basically took compressor oil, POE, PVE, and mineral, all of the same viscosities, ISO 32, and we cooked them inside of the base of actual compressors that we cut out. We put them on an induction cooktop. We thought it was fitting. So we have a steel pot that I bought so that we could actually cook oil in, and I said, you know what, screw it. This looks really cool and also is more realistic if we cook it in the base of an actual compressor. So we were actually really surprised with the findings that we found today when you actually cook oil around 340 degrees. So when we talk about discharge temperatures out of a compressor, right, we talk about discharge superheat. We don't want high discharge superheat. We don't want crazy high discharge temperatures, just like we don't want high suction superheat. The question now becomes, compressor cleanup. Really, do I need to do a cleanup? Like what takes place when compressors go into those high discharge step downs and they trip those error codes associated with actual high temperatures? What's actually taking place? Can I just change the compressor out and go down the road? And today we were testing that theory because, again, I've never done it, and I don't know of anybody who has done it, actually cooked oil to see what happens at those higher temperatures. And we only did it for 5-10 minutes, but we were surprised about the amount of carbon that we found, the amount of contaminants that it actually creates in just such a short period, that it's really astounding because, again, we think about those systems and how much they run out in the field, and they could be running for days, they could be running for weeks with high discharge temperatures due to whatever, refrigerant restrictions, undercharge.
Right.
A lot of those things that add up over time to where these systems are exposed to those conditions a lot. And so you see these guys who look at the operational data and they're like, my discharge temp sensor, which is like, 6 to 10 inches downstream, they're like, my discharge temperature is like 310 degrees. And, I'm not worried about the oil. We're just going to change the compressor. And it's like,
it's oil, right? That's what oil's supposed to do. It gets hot and then cools off, right?
Oh man, it's so cool. So the science behind it's really cool. But yeah, so I mean, the findings that we found were interesting. That they were different than what he thought and different what I thought too. So Yeah,
It was a hot topic. I never thought I'd be here in Florida with Roman, dealing with pot, and it was smoking. We were smoking pot, technically, scientifically.
it's a good thing we don't have any sponsors. So if you're listening to this and you want to
Yeah.
sponsor our podcast, please reach out to us. He's been
So
hitting me with these jokes all
what,
day. I'm used to him, but no, you don't.
I mean, it drives back to something that we talked about in the first two episodes, is like hot topic items, and you kind of said it jokingly, like I got a discharge of 300 degrees, but in my mind, when I'm looking at one of these VRF systems and I see discharge temperatures approaching 210, 215, I'm at the point to where I'm thinking we need to slow this thing down and stop it. So
Yeah.
what two things come to mind, right? As you said, we're reading that temperature 6 to 10 inches away from the compressor. What do you think the difference in temperature of the oil is in the sub basin of the compressor versus what's reading downstream, right?
Yeah.
We're probably
Yeah.
significantly warmer.
Yeah. Well, we talked about that too a lot today. Was just that, and Ty had a lot to say about it. Just that how high the temperature actually gets into the internal components of the compressor, because there's a lot of meat and potatoes in there, right? It's not just the outside casing. It's not just the temperature of the refrigerant leaving the compressor. You have to think that it's somewhere close to 50 to almost 80 degrees higher at the center of the compressor, where most of that mass is, where most of that oil is, where most of that friction is at the scroll plates. And so, what do you?
Well, I used to work for a major compressor manufacturer, and they had an exact number that if it was 225 on that discharge line, they had an exact number of 300 and something inside the compressor itself. And if it's a reciprocating, where you have that piston coming in, right there at the top of that piston, at the bottom of that valve plate, that's where all of your heat was gathered up. And then, of course, at a scroll set, at the end of those scroll, that's where all that heat is. So not only the oil itself is breaking down, but you also have to think about, those check valves and any other metal components that are right there, or, relief valves or any other moving parts. All of that is going to be susceptible to that heat.
Yeah, and the other thing that our experiment didn't account for was the windings, the electrical wire, other things that you're going to find inside of a compressor. So we literally just cook the oil for the sake of cooking oil in clean compressor bases, right? We clean them with RX11 flush and make sure that they're good to go. But even just cooking that oil by itself with no other contamination, with no other outside things messing with what it is, we were surprised to find that one, carbonation took carbonation. Yeah, it's a soda now. Carbonization. There we go. The buildup of actual carbon in the oil is a real thing, and it looked different per the oil. So mineral oil, what we hit it probably 250, 270 started to smoke.
Yep.
And then we got to that 300, 310 range, and we actually got big carbon flakes that built up at the base in just the pan where it was closest to the actual heat source of the compressor. Then we got to POE oil, which actually was really hard to smoke. We got to like 300 to 325 before we could get any smoke out of it. I think the flash point for that was somewhere close to like 346. I've been misquoting these numbers all day. So
And it stank really bad when the POE was spoken.
Yeah, I'm
It was
sure.
like, whoa.
yeah, it was rough. Yeah, it was
bad.
just like the mineral too. The mineral was actually really bad too. And so, but for that one, we saw some contamination take place. The mineral oil, it went from clear to yellow, which was really cool to watch. The POE actually went from like a clear color to maybe like a lightish brown. It was really hard to see any kind of extra contamination on there without a lot of volume in the container. But there was still flakes that were present in the actual oil. The one thing consistent between all three types of compressor oil is that high temperatures at 300 to 346 degrees, which is what we exposed them to today, for 5 to 10 minutes was more than enough to create actual contamination in the oil, right? So we talk about what happens to compressor oil when it breaks down. It does exactly this. Particles, contamination, the oils start to separate at a molecular level. Now they can no longer lubricate like they're supposed to, and so they lose those anti-wear properties. And when that happens, now we're talking about causing damage to bearings, sleeve bearings at the top and bottom of the compressor. We're talking about doing damage to the sleeve bearings at the base of the orbital scroll in the actual scroll compressor. We talk about scroll plates, milling down scroll plates and creating metal slurry that builds up on the magnet core of the actual rotor of these compressors. And it's just a really bad disaster. And so to that point, it's like looking at something like that, saying, it's okay. I mean, you really can't after seeing what we did today.
The first thing that comes to my mind when you're talking about this is right. It goes back to what I asked earlier. Is like in airflow, we're always worried about how much extra heat that fan motor is going to put into the airstream, and I don't think anybody's really, I personally haven't thought about it. It was like, how much heat is this compressor actually putting into my refrigerant stream? and the oil is in that. So yeah, this is a really cool topic that I don't think anybody explores this when it comes down to like what potentially could have hurt my compressor, right? We often think of like lack of refrigerant or installation issues or you know the low hanging fruit of what's killing these systems, but if they're running really hot and we're getting carbon buildup at, you know, some of the normal temperatures that we're seeing, you know, is it not so much an installer's fault? Did they not braze? I mean, how many compressors have I dumped out and seen just jet black oil and said, you know, we did everything by the book, we purged and we did everything by the book, but this thing is cooking compressors, and like literally, it's cooking them. This is a really cool topic, guys.
Yeah. Yeah, and so, and again, you know, we talk about VRF a lot, and you know, we have Ty here today, and he can talk to the other things, you know, the things that I don't know a whole lot about growing up when mineral oil was a big thing, right, with R22 and the things that they saw with that and the POE. So I'm gonna let him take it away in regards to the progression of oil in compressors, because that's a lot to have to do with build up this story to get to where we land with PVE and why cleanup is so important. So.
Oh, so back in my day,
Back in my day
when all we had was mineral oil, and it was the best ever. And it was like I loved mineral oil because it was so indestructible. People talked about how great R22 was and back in the day, but really more than R22 was the mineral oil, because when we transitioned over to POE oil, it's not forgiving. Like we were supposed to follow these rules back with mineral oil, but POE oil being hygroscopic was huge because mineral oil would turn to acid with enough heat, enough moisture, but it, you know, it was forgiving. You could get away with these bad habits. You could get away with pulling a bad vacuum. You could get away with stuff. It still wasn't good, but you could get away with it. With POE, you can't. Like it literally turns to an acid. Yeah. But one thing I was not expecting, my love of mineral oil, was seeing how the mineral oil broke down faster at a higher temperature and the POE didn't. So I was completely unexpected with that. And then also some previous science I've done of some exploring is that POE oil transfers heat faster or better than mineral oil does. So that's one of the reasons. So when you got to think everything in the system is coated by oil, especially in the very bottom of the evaporator tube, you're losing heat transfer. So by having POE oil, you actually transfer heat better and makes the system a bit more efficient having POE oil. Now, you know, the fact that it absorbs moisture, hygroscopic, and turns to an acid is a huge issue. I think that's the biggest issue we have, which is one of the reasons I like PVE oil, because you don't have that issue. And then also, the PVE oil handled the higher temperature way better than the mineral oil did. So I'm now a huge fan after today, a huge fan of PVE oil. I'm sold on that because there's still stuff we're going to test, but I was just super impressed with the fact that it didn't absorb the moisture like that, and it handled the very high temperatures very similar to the POE oil. So that was pretty cool.
Yeah, and even then, not all oils are impervious to temperature. And so, you know, with mineral oil, we saw the smoking occurring at 200 degrees, whereas the other oils, they didn't start to smoke until we hit about 300 to 315. Wow. And so even with that, you have to remember that every oil has its breaking point. And that's the point, right? The point is not just to say, hey, you know, scientifically this and that and, you know, oil and smoke. No, we're talking like, you know, oil has a life expectancy, and you shorten that life expectancy when you cook it, right? When you cook it inside of an actual compressor. Because let's be honest, the hottest component in any system is going to be the compressor, right? At any point in time. Well, hopefully at any point in time. But that's the premise here. And so when you hit a specific temperature, and I tell people this all the time, and they're like, yeah, whatever. You know, when you see that 257 discharge temp, that compressor is cooked. You have to clean up the system now, right? The amount of damage that's done to the oil that's contaminated, that's left the compressor, that's gone through the oil separator, that's gone through the evaporator coil, that's inside of the system itself, you're not going to get that out. And even though you put fresh oil in there, getting that oil flushed out of that compressor into the rest of the system and bringing the contaminated oil back is a real thing. And so the only way to mitigate that is, again, doing that compressor cleanup procedure, which is where we're putting filter dryers in temporarily, cleaning up the refrigerant, and then bypassing them and testing the oil. Right, that's something we haven't done yet, is actually do oil tests on the oil that we've cooked here to see what's actually changed and take place. So
were you guys adding actual moisture into it, or just letting it it's take
Florida,
from the atmosphere?
So
Okay.
Once you pop
pour water in the mix, that'd be a different topic. Yeah, who knows? But back to kind of the conversation on mineral oil into the progression to POE and PVE is like, do you think that the size and complexity of the systems that we're designing now has kind of led to that change towards different oil?
Well, I think the initial change was the fact that the refrigerants that we have wouldn't carry mineral oil anymore. So
Right.
that was the big thing. They had to pick something else. They had to go with something different just so we could get the oil to flow. I mean, we know what happens when we don't have oil return to a compressor and it's all in the evaporator.
Yeah.
So it was a must for that. The other things about the energy efficiency, I imagine that's very minor overall. The fact about temperature change and all that, it's overall minor. These are just fun little extra facts for it. And I was not a fan of POE oil, but now have a little bit more respect for it after seeing. I knew about the heat exchange, but now seeing how it handled that heat a lot better, like I have a lot more respect for it. It's like, you're still not my friend, but like, I can respect you now.
Yeah.
But now after seeing PVE, I'm like, we know that it will flow with the refrigerant. It will carry back. It does have good heat transfer properties. And the fact that it handled that heat really well, it's like a champ. I'm like, whoa, you've earned my respect, Mr. PVE. Hats off to you.
Yeah, well, and to that point too, and we were just talking about this earlier. Idemitsu, I think, is the original patent holder for PVE oil. They have a few studies out there that show you the difference between PVE, mineral, and POE, and one of the main properties that makes PVE shine when compared to those three oils is its inability to actually clog or coat capillary tubes on the internal lining. And so when you think about high blood pressure and a heart, trying to pump blood around your arteries and your veins that get clogged with cholesterol. The same thing happens when we go. No, I'm not talking about you at all. But I saw what you had for lunch, Ty. Okay. No. But with actual, PVE oil, we're talking about, they added a bunch of stuff to it. They added, I think they added some like motor oil to it. They added some transmission fluid to it, and they still found that the way that the oil operated and lubricated the system, it didn't affect it at all, right? So it handled contamination much better than the other oils that it was put up against. And so when we talk about VRF and VRV, we talk about systems that have a lot of capillary tubes. We talk about oil return line. We talk about the hot gas bypass, or even a few other spots on the four-way valves, bleeding those capillary tubes and bleeding refrigerant back to the system, and even pulling oil out of the bottom of the accumulator. And so it's extremely important that we don't clog those things up over time due to insufficient practices like not purging with nitrogen rebraze, not pulling a deep vacuum, or even having so you can pull a deep vacuum, but again, not following the correct process for the decay test, right, to ensure that you've taken all the moisture out of the system and dried it out thoroughly. Because again, like Ty said, POE and water, it's acid, right? And we all know what happens to acid in a system. It eats the windings, it eats the scroll plates, it eats a lot of things. So
it's not the same. I don't want that.
It's a good analogy to think of the compressor in your systems as the heart, right? All those tubes and capillaries are the veins, right? If you got clogged arteries and clogged veins, your heart's not going to last forever. So it's a good analogy.
Well, also, if we think about an engine, people think about engines wear out. Like, how much you take care of them, you can extend them, but they will essentially wear out because you're bringing oxygen in from outside air in with nitrogen. Other contaminants are coming into that engine. Your fuel has outside sources with other contaminants coming in. You have all this. You have literally a fire or explosion, lots of heat you have to deal with, and then you have all these byproducts getting into the oil and going through the valves. On a refrigeration system, it's a sealed system. So if our refrigerant's pure and clean, there should be nothing in there that's a contaminant. Because the refrigerant's cooling the compressor, it should not be overheating. Because the oil is not getting dirty by any byproducts, the oil should never get contaminated. So really, the moving parts of that compressor should always be lubricated. If we have the correct voltage coming to it like we're supposed to, that compressor should last forever. And I have some antique compressors at the house that are, from like the 1920s that are still operational. So the compressors itself, they should continue to last forever as long as we keep it a sealed system, as long as we don't overheat it, as long as we keep the moisture out. Those are the key things. And as we have technology to where we're getting those higher compression ratios, such as these low cold climate heat pumps, to where now we have more challenges. We have that high compression ratio. We have to deal with the heat again. So now we're having to do other things, such as like add the oil pump that Roman was telling me about today, about having the actual gear oil pump. I didn't know that. I learned that today, which is super exciting. So these are the things like, hey, we have to make sure we keep that oil lubricating in the whole system. So as we add more technology, we have more solutions to overcome it. But it still comes down to oil. Keeps it clean, keeps it working.
Yeah, I know. He was talking about the there we go, the actual oil pump for an LG VRF compressor. It's like a worm gear, essentially.
Why am I not surprised it's on your keychain?
I keep souvenirs from my kills, okay?
No, but that's I mean, cars do that all the time too, right? Think about how we have to get oil back up into the pistons, right? So yeah, there has to be a pump sometimes, right? We can't rely on refrigerant alone in most cases, specifically with our VRF systems, right? We have modes of oil return, but just because it's coming back doesn't mean it's getting to the place it needs to be, which is, in our world, it's on the top of the compressors. We have to bring the oil back up. So having a little rotary pump like that to force the oil back up, I mean, that's the same thing as having an oil squirter in your piston.
Yeah, yeah. Well, and on top of that too, when we talk about oil and oil lubrication of the actual system, there's a lot of things that we have to think about as well. And that's not just oil return; it's also keeping the oil in the compressor. And you're going to find a lot of that becomes difficult. So we can talk about, getting the system right, getting it cleaned up, getting it to where it should be. But then the other side of that equation is, okay, well, how well are you maintaining that system? Because as soon as we get filters clogged on all 12 indoor units connected to the system, you're going to start seeing that flood back come back. You're going to find expansion valves that fail. You're going to find temperature sensors that aren't reading correctly and cause the valve to open more than it should and let liquid refrigerant come back down the suction line. And so these are things that are going to cause displacement of the oil out of the actual compressor. Then you get into the side of refrigerant leaks over time from not actually maintaining your system and checking it thoroughly, and that leads to a lack of oil returning back because volume and velocity isn't there to return the oil, like we've talked about many times with oil return cycles. And then overcharge, and that's just people not doing the due diligence when they start the equipment to ensure that the charge is correct, and they just toss a few more pounds in there because the suction line's not cold. And that results in, when it goes into those oil return cycles, that it actually turns those oil return cycles off prematurely before it gets any oil back, because it gets liquid back. It thinks it gets liquid back from the actual all indoor units to get that oil back into the compressor, and instead it only gets it from the first fan coil because it's so overcharged, or it gets into those high pressure step downs where it can't get to the speed it needs to get the volume there to get the oil back.
Yeah,
and all those things combined together, result in
a fine ledge between having too much and not enough refrigerant, to where the perfect charge allows for the correct flow, the correct velocity of our oil to come back. Too much, I mean, we're just going to stack liquid. It doesn't mean that you're going to move that refrigerant. It's just sitting there. So that's a good thing to put out there for guys, is like, specifically on our VRF systems, right? Like, we can't charge these things, beer can cold. We can't do it on these because it's so much different.
It's about 10 pounds and a half.
It looks good. Right. I mean, and I'm not here to say that a VRF system is a critically charged piece of equipment, but it is an engineered system to where the charge should be dialed in 100%. To maintenance, right? And this is where our service tools come in. Is this should be part of a maintenance bid. When you're doing maintenance on these VRF systems, you should be plugging in. You should be getting all the information that you can out of this system to verify that it is running properly. Doing these cleanup procedures, like, I'm segueing into another topic. If we want to talk about maintenance, like, if we have a compressor that goes out because of, it goes to ground or it leaks or whatever it is, when we get to this topic of a compressor was overheated, now we have carbon buildup, how fast or how much time should we put on this compressor to say this thing overheated? Does it need to be replaced? When we have grounded bearings, like, or grounded compressor, then yeah, we got to replace it. But if we had, say, an inverter failure for overtemp, and the compressor megs fine and it seems to be okay, and we go run it with the charge, and then we find out that this thing is running 210, 215 degree discharge, should we replace that compressor?
I really wish we had an oil samples, so we could get an oil sample like we do in commercial. We could get an oil sample, we could have it tested to see exactly what's going on. We could test it for acid easily, organic and inorganic, and then we could also test it to see if there's carbon buildup in there.
Yeah.
To me, that would be, a great solution.
And again, to that point, like, okay, so then let's take this a little bit further than that. Okay, now 215, maybe it's not going to be a crazy bad issue, but let's talk about the obvious ones where the compressor turns on and in literally 2 minutes it hits 245. Right? And I've seen a lot. And it's like, well, yeah, no, that compressor is toast, right? Because again, that high temperature that quickly is a clear sign that it's operating irregularly. It shouldn't climb that quickly, right? That there's literally no oil in that compressor, and it is metal on metal 100%. Yeah. And so the risk of leaving it the way it is and just hoping if I add more oil I can take the discharge superheat down and it'll be okay, it's not. Again, we cooked the oil for 5-10 minutes today, and we literally created contamination.
Yeah, that's insane.
5-10 minutes, like that happens in a blink of a second out in the field.
Yeah, I mean that could be the difference between your service checker updating twice. right?
That's what I'm saying. And so the fact that we're even questioning if we should change it, again, does it suck? Yes, it sucks. But again, something caused it to get to that high temperature, and that's not the point. The point isn't just saying, okay, let's change the compressor because Roman said it's bad and the oil is contaminated forever. We're saying that it died for a reason. Find the reason, right? Should you change the compressor? Yes. Should you stop there? Absolutely freaking not. Right?
No.
You should go in deeper. You should dig deeper. You should find out what killed it in the first place. Because if you don't, then don't even change it at all. Just let it die of natural causes over time, and then come out and change it maybe, or let someone else change it. If you don't want to do the work, let somebody else do it. Right? Get me all worked up about this topic.
No, I mean it's a valid topic, and it's something that I live kind of every day. Being in the position I am is I want to tell people that no, their warranty is denied because what did you do to figure out what was wrong? Why did your compressor go to ground? Why are we burning this thing up? Oh, well, the error code is this. Well, that doesn't indicate that's what the root cause was, and kind of one of the things that I want to advocate is we got to do root cause analysis. We have to trust our technicians to get to the bottom of this because we'll be honest. Compressors and inverters aren't cheap. Doesn't matter what brand you're working on, if it's residential or if it's commercial, it's not cheap. So replacing this thing just willy-nilly because I lost a compressor and not doing any analysis on it, you're doing a disservice to your customer.
Yeah, it's expensive.
Recently, there was a post on social media where they had a screen that was completely clogged up. And everybody was saying, oh, they didn't flow nitrogen, which, is a possibility. But my thought was, what if it was cooked oil? What if it was, and then we did this, now that we've done this, I'm like, it could have very well been. So we really need to look at that and see if, what the difference is. Because if that was a cooked compressor, then it's another symptom. We have dead compressor symptom, we have clogged screen, which is a symptom. So what was the root cause? Was it somebody not flowing nitrogen, or is there something else that cooked that compressor?
But here's the point that I want to make. The solution is the same. You change the compressor and you clean it up, right? You add the cleanup procedure. So we can sit here and we can split hairs, and we're going to do more testing and we're going to get to the bottom of it to find out what's what. But the point is that if you don't have the time to do the test, if you don't have the ability to do the test, and your company doesn't want to pay to have you do the test, you can still clean the system up and get to the same solution, right? You don't have to know exactly what it caused. Just know that this solution fits both cases, right? And that's the whole point of it. Because you're going to get people who are still going to say, well, I don't do compressor cleanup procedure and I don't need to. And it's like, well, I mean, we cooked oil for 5 minutes and I can tell you that you need to. Because again, the real world scenario is going to be 5-6 days of this being cooked like it is in multiple situations and scenarios. And so, that contamination just goes all throughout the system. And it's not a lack of engineering. It's not a design flaw, right? And the design flaw is that we didn't do the due diligence the first time we installed it and started it up and actually charged it. And so it's just one of those things where, sure, we could sit here and we can split hairs to find out, chicken and egg. But again, the solution is the same. Yeah, clean it up.
Now, we talked about the carbon and cooking it. I want to talk about also acid.
Yes, acid. So the likelihood of finding, this is the misnomer. You see guys who go out to jobs and they change out compressors and they take the little shaker bottles and they shake it. There you go. Shake it. Shake. And they say, well, it's no acid, so we don't need to clean it up.
Or, even worse than the pink fluid is the little blow and goes. The litmus paper, right? Like.
So just think. So here's the misnomer, right? POE, we've been trained to know that moisture creates acid. There's no fighting that, right? That science says very clear it creates acid. With PVE oil, it does not create acid in most cases. Now, there are situations where a high enough moisture content within the system will still create acid. Yes, I'm not saying it won't, right? I'm not saying it can't. It can. The likelihood of it creating acid is very, very slim. So if you're a technician who's actually using that as your test to determine if you need cleanup or not, you're missing the boat. Yep. You're missing half of it, right? There's the acid side, then there's the contamination particle count. Right. And so there's a reason we use Trico oil samples. I actually have oil sample kits. I don't know if I've told you this here or not. It's not here, but I have them in my truck. We're actually going to test the oil today. And so with that, we send it off to the factory, and there's a lot of companies out there that do oil testing, and I'm not saying that their oil testing sucks, but I'm kind of am, low-key, not really. But if you're only testing for organic and inorganic acids and moisture, you're also missing the boat, because again, we should be counting particles at different micron levels. Because the oil that we cooked today, we found the longer that we cooked it, the more particle count that we found in the actual oil. And now they all look different under the microscope as to what they look like. But what we found still, it's something that you should be measuring. The longer you cook it, the more particle count there's going to be in that contamination. And so, again, if you're just looking for acids and moisture, you may still think that your system is good because of the test, when really the test should also be testing particle count, right? How many particles did they find? At what concentrations? At what micron levels? And Trico does all of that very beautifully, might I add, for $45. And they're not a sponsor yet, but they might be. But it's one of those things. So, these are... we can sit here as technicians and make excuses to why we can't do the best practices. But for $45, I would rather know how bad is this contamination, because it's also another nail in the coffin to show the customer, hey, here's where we are with contamination. Let me do another test and find out how much did we actually clean it up. He's actually going to pay me $45 here.
I'm sold. You had me sold. Let's test it.
But
it's good.
Like, why not? Why not?
No, I mean, how many times... I can't count how many times that we sell a compressor and then a week later, like, hey, this thing died again. It's got to be a problem with the compressors. I mean, the logical brain in me says, hold on a minute. You put a compressor in, and then in less than a week, it's already died. What happened? Oh, well, it's a bad compressor. Obviously, it's a bad compressor. What happened? Did you test anything? And yeah, sending an oil sample out is invaluable. $45 is pennies compared to what the information gives you. But the bad part is, and this is a plea to VRF manufacturers, give us a good way to get oil out of these systems. Give us a tap.
Please.
Give us somewhere to get oil out of the system.
Please. Somebody who's listening. Yeah. Just give us a tap on the side of the compressor, somewhere in the suction line. Thank you for tapping my shoulder. And just something somewhere, or some kind of device in the system that's designed to collect oil over time that I can just go pull from. Because now we're doing things like the great HVAC company out there, right? We talk about them a lot, and Ken Jones, where they actually put the filter cleanup dryer assembly on there, and they put a drop leg. Yeah. Right? So you're like, wait, how do I test the oil? How do we get the oil out? Am I going to just blow it all out on the roof? No. What you can do is, when you're going to put those cleanup procedures in, you can actually add a T with a drop leg with a Schrader core at the bottom on the suction line. Remember that oil is going to follow the natural pathway of gravity to the bottom of the suction line, and over time that little drip tube will actually fill up with oil that you can actually pull a sample out of to get to what you're trying to do. Because again, testing it before tells you the particle count. Testing it after shows you if it is cleaned up and how much have you improved it, and if you should continue to filter the refrigerant and change your cores, because that's the other part of it too. Do I need to keep going with this? Right? How bad is it actually?
Right. So yeah, the standard, do you have a split across your core? I don't think is a very good standard, at least on a large VRF system. It could take weeks. It could take up to, I think the longest one that we've had is about 2 months. Of consistent core changes every 3 days to clean it up, and it was bad. It was really bad.
Yeah, that's crazy. That is crazy, and they do catch it eventually. Now, that's the other thing too, where people are going to say, "Well, you cleaning up the system doesn't actually clean up the system," and it's like, no, okay. So from the factory and the type of oil that we use, any refrigeration oil out there, including vacuum pump oil, you can't get it back to the original factory standard, right? It's not going to happen. That's laboratory conditions of how they refine it and what they get it to. However, we can get it to the point where it's no longer a mitigating factor to failures. And that's the whole point of this. You're never going to get it clean, right? Quotations here. You're going to get it as close as you can to where the system can now live a long life without having to worry about the contamination being a factor in the failures moving forward. Yeah.
So is there any other enlightening things from your oil cooking experiences today? I mean, the carbon buildup, that's something I never thought of, but that's really cool.
I would like to go on one more thing about the acid.
Yeah.
Because back in my day, we had acid, and we just there's acid. You just buy this magical oil neutralizer, and you magically put it in, and it just made the acid magically go away. And it wasn't until way later in life, and I'd already contaminated a lot of systems before I learned the truth behind that and that to acid neutralization is a chemistry project. So you have to know exactly how much acid you have, and you add the exact amount of base. And we never know how much acid we have. We can't measure how much there is quantity in the system to neutralize it with the base. And a lot of people don't realize that base is very powerful. The coil cleaners, some of the most powerful coil cleaners we have are a base, and it will eat a coil away.
Yeah.
So if you put the wrong amount of base in, you already have an issue. But going back to the chemistry side, I didn't know this for a long time, is that when you add the base to it to neutralize the acid, it's now neutralized, but you end up with a chemical process where you get H2O, water, and also salts. So now you have salt water inside of the system. So yeah, you don't have acid anymore, but now you have salt water in the system. And guess what the water is going to turn back into?
Acid.
And now you have salt also. And so I talked to a manufacturer about this, and I was trying to remain calm, but I was very, I get passionate about things.
Yeah.
And they were saying, well, yeah, but your filter dryer filters that back out. I'm like, then what in the blink is the point of having this product if you're going to use the filter dryers anyways? I was very animate about that. So it gets me riled up today.
But I mean, even to that point, right? So when we talk about opposite ends of the spectrum, and I wrote a tech tip about that recently with Rachel Geiser. She's a brilliant chemist. She runs circles around me all day long. And the way that she explained it, it made sense. And so, on one end of the spectrum for the pH scale, you've got acids, which we know are bad, right? You could dissolve people in them. If everybody's watched Breaking Bad, it happens, I guess. But then on the other side of the spectrum, you've got a base. And so these are two opposite ends of the spectrum. And when they collide together and you bring them together, they neutralize each other. They create a neutral harmony. But to Ty's point, there's no way to find out exactly how much acid you actually have in a system. And so what's the problem there again is leftover base. If you have leftover base after neutralizing the acid, it's just as bad as the acid. And it's like, so now we're actually causing more problems by introducing something like that in the system to try to clean it up and get the salt water out of it. And that we could still be left with salt water. Let's say we get it out of the filter dryer, we're still left with base. And it's like, well, is it even going to get out of the system now? And there's no telling it. So, and to Ty's point, growing up in the trades, changing out compressors at the age of 12, I just remember tipping that compressor back and just, chug a lug into the suction line, right? Because that's what we did, right? It had acid, right? It smelled it, so you just here you go, compressor, here you go.
Made it go away.
Yeah, this is gonna make you feel so much better. It's like cold medicine.
Which reminds me of all those posts on the social medias of like, we've been doing this for 30 years and it never had a call back. Well, they didn't call you back. That's why.
Right. And that's the thing, though, and that's the beauty of science and chemistry is that you don't know what you don't know, but science is pretty clear about a lot of things. And so when you look at the chemistry behind it, when you look at the molecular makeup of the oil, when you look at what happens to these things, not only when you apply pressure, but temperature and other contamination, these are real factors that take place inside the system that can cause long-term problems. And you can't just sit here and ignore it, right? The science is very clear. And you could try. Maybe just talk really loud. No. But it's one of those things where, best practices are following the flowing with nitrogen when we're brazing. We're talking about dehydrating the system 100%, and then cleaning up your oil after a compressor has failed. And I hate to say every compressor, but I mean, let's be honest. Unless there's some kind of mechanical seizure due to a screw being sucked into the compressor, which apparently I guess could happen, according to some manufacturers, it's just not likely. And so you kind of have to take that systematic approach of understanding, hey, what does this cost if I don't do it, right? What is that cost? And that cost could be associated with more failures. And how many times do you want to change the same component before the client moves on to somebody else? Do you want to lose a client over it? Or would you rather just test it and figure out what you're dealing with and then make the associated changes to do that? So
I think it's going to make me a bit more skeptical when I see grounded compressors of, was it an electrical issue, or should I be looking at, like you said, the buildup of medical particles from, the scroll coming apart? It's gonna create more work for me, I think, but I'm okay with that because I don't want more failed compressors. I think it's silly that we have the amount of failed compressors we have out there.
And VRF's got a bad name for it, and I hate to see it because I love the technology. I love the equipment. I love where we're going as an industry, and obviously we're going to start moving over to propane as a refrigerant. We're going to start moving over to CO2. Yeah, I can't wait. And so as we evolve in the industry, and VRF isn't going anywhere, it's something that's here to stay. And so for that, we have to understand all of the moving pieces that we have a part of this, and also what we're working with. Because again, Daikin may be one that uses PVE oil, but Mitsubishi is still using POE oil in their inverter compressors for VRF. And so it's all about understanding what you're dealing with your particular piece of equipment and how to address those concerns or issues within the system. So
Yeah.
it all adds up, man. And it's just one of those things where you don't really know until you see somebody like us, a couple of hillbilly rednecks who love HVAC, cooking compressor oil in actual compressors on induction hot plates. So
Breaking POE.
So I got a semi-related question. What about the use of like PAG oil, right? So in automotive, right, we either had mineral or PAG, and we were using the PAG on like the 134. But the interesting thing about PAG is it looks like it's going to start coming shipped with the 1234YF. Do you think we'll see the introduction of PAG coming back?
I have no idea what that even is, to be honest. So PAG oil, what is this? I mean, what does it stand for? This sounds like a made-up
Polyethylene
thing.
glycol.
Oh, polyethylene glycol.
Polyalkylene.
Alkaline, sorry, not ethylene. No, I would be surprised. I mean, again, we're talking about when we make changes in our industry to different types of refrigerant, you have to remember that we have to then tag the associated things that work with it
Right.
into the system. That gets worked in regardless, and that's not only just components like A2Ls. We're dealing with refrigerant sensors now. That was never a thing. Refrigerant leak detection was just something that you bought, from a manufacturer like Fieldpiece, and you went out and you tested a system. Now we're having to have sensors installed from the manufacturer side to mitigate, potential risks and issues in the field. And so I think as we change, again, if that is an oil that works with that specific refrigerant, then I would see it being a thing that's going to pick up here in our industry. Again, if that refrigerant becomes a staple for a specific product, let's say refrigerators or low temp freezers or something like that, then I definitely see it being something that we need to know more about. Because clearly, right now, I've never even heard that word before in my life. And now I'm going to go look it up because, again, I'm super interested in the differences and the changes that we make and how we roll through it because, as you can tell, although they may be refrigeration oils, they have to be treated differently. And they all have their quirks, right?
Yeah.
Mineral oil likes to smoke at a low temp, right? It's the bad oil, right? That bad oil. And it changed colors actually pretty quickly. It turned very yellow. It had the most carbon buildup. Clearly, its mixability with refrigerants sucks, which is why we changed. And then, POE, it didn't smoke at all. But again, it still had the same amount of contamination. And then we have that acid factor that we can't stand. That does cause a lot of problems and failures. And so then we move over to the final destination of PVE. But maybe PVE isn't the final destination. There's going to be another oil out there, I'm sure, as we transition to maybe CO2. And I would love to hear back from a lot of people who are listening to this if you know something that we don't. Because again, as we change refrigerants, we're going to have to match those refrigerants to the oils that perform the best with those refrigerants. So I definitely would see that being a thing. So
It's very cool.
yeah, and so with all these things, with best practices, we can go through the industry and talk about theory and say, I read it in a book, or someone told me, or someone said something at the counter of the distributor, right?
Parts counter man. He's the smartest guy in the field.
Just like all that propane that's in the A2Ls, and so. But here's the thing, until you see somebody like us or somebody who actually shows you the physical hard evidence of the repercussions of why it matters, what takes place, it's kind of really hard to, sit here and say, well, I just can't do that. Still not going to listen, la, 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 la. Like, everybody's going to know. And the more common knowledge, the more we talk about things like this and just put our foot down and say, listen, we know for a fact, we watched the oil change on this video here. We can't ignore it anymore. Like before, It was just like, don't do it. And it's like, okay, well, someone said don't do it. I don't know why they said don't do it. They just said don't do it. It says it in a book that says don't do it, but that book's like 30 years old, so maybe they have no idea what they're talking about. Fred at the counter says also don't do it, but I don't care what Fred thinks. Like that guy's made some poor life choices. And so here we are, and it's like, no, we're saying don't do it because watch the video. We cook some oil, and look what happens. You can't ignore it anymore, right?
I can't wait to watch that. That's really cool.
Yeah,
and that's just oil. We still haven't done anything with the windings or any of the plastics. At what temperature they might add.
Yeah. So now the goal is to cut. Now the goal is to cut the top off of a compressor with the windings still intact, and then cook the oil with the windings and make like a nice little stew. of actual compressor. So here's the thing with the scientific method of testing. We tested in a controlled environment without any extra components in the system, and we didn't get the outcome that we thought we would. And so now we're going to test it by also cutting the top of the compressor and cooking the oil with the windings, with all the components inside, with everything that you would naturally find in a system, and see what changes, right? Does it stay the same? Is there more contamination? Is there the yellowing color that we see in PV oil? Is that really leak dye, or is that just what you get as a byproduct from the coating that they put on the windings when you cook it at 300 degrees?
Yeah, I would say to me, the one thing that I'd worry about is the enamel that's on the windings of the coil. Is like, what happens to that? Because enamel does have a heat rating. It's not going to last forever. Specifically, the stuff they put on compressor windings or any windings of that sort is, microscopic. So it's not going to last. It's pretty cool.
And the plastics and the bands that they use to hold the wires together, and the separation between the two. It all adds up to a point where it's like, how much of that is actually a factor.
What about specifically the refrigerant itself under these heated conditions? Do we think that it has a factor of breakdown as well?
Yes, refrigerant can break down, especially when there's arcing going on. Electrical arcing is what causes it to break down. Temperature, not so much, but arcing, absolutely. And so when you have the arcing breaking down of the refrigerant itself, you end up with hydrochloric acids, hydrofluoric acids, and that's where that comes in. And when you break down, like, for example, the difference between an HFO, when you break an HFO down versus an HFC, you end up with two different types of acid, and they smell extremely bad when it does. But that's typically when you see electrical arcing specifically, because it takes a lot of energy to break it down. But yeah, it does break down.
Yeah.
And those are things that we have to consider when doing compressor cleanup. Again, we can sit here and split hairs as to what the type of failure it is, but again, the solution is the same. It's filter dryers and not using an acid neutralizer. Although you may want to.
And mechanical failures cause electrical failures. So when I worked for a major compressor manufacturer, they were telling us every tag came back, said grounded, electrical issue, and they would open it up and they found out it was a mechanical issue first. And once it got locked up or wasn't moving, your bearings went out, or the rotor inside has so much play because the bearings are gone, it starts making contact with the stator and the windings. Then it always come back electrical, and so the majority of it was mechanical due to one of the 5 causes, and then everybody write down electrical. So it's just electrical was the final symptom.
Yeah, I know, and I've had conversations.
It's a measurable thing, right? Because you put a megger on it and say, yeah, I'm to ground, but how do you know that the bearing is shot without ripping that compressor apart?
How do you know it didn't seize first, and then once
exactly.
it seized, then it overran?
I got a compressor that I want to send to you that I'm pretty sure the scroll broke off the shaft.
That's a good one. Yeah, again, it's one of those things where, and I cut one open recently too that was actually electrically grounded, and you could see the arc pathway from the windings, because it was a turn-to-turn burn, which is really fun to say. But it was so between two actual windings, between the rotor and the stator, they actually overheated to the point where the enamel had worn away they arced out between the actual turns. And so that arcing, you could actually see where it had burned the oil in a lightning path all the way to the casing across the actual housing mount of those windings. And so you could see the path that the electricity took, and the electrons through the actual casing that drew this black lightning across the side. And so yeah, it was pretty cool. It was really good.
And so when they make those motors, the windings on it, they have they're allowed a certain amount of inconsistency with that enamel. So, and they said that to the guy that I talked to, the engineer I talked to, said if you get unlucky enough to where you have a little nick on the winding here, and then you have another nick on the winding here, if you get unlucky enough for those nicks to actually line up, then you have a turn-to-turn short, a turn-to-turn a problem in there, and that's where you end up with that turn-to-turn winding. It's specifically used on a new compressor. You just got unlucky enough for those 2 points to line up, because if you have a nick in a wire, but the other wires are insulated, so it's not an issue. But when they line up, then
But that's the thing, right? So when you talk about inverter compressors, especially in VRF, you have to remember we're doing neodyne magnets on the center of the core, right, for efficiency purposes, for added torque, right, inside the actual compressor, and use less electricity to actually, move that rotor. And unfortunately, when you have contaminants like copper shavings or metal shavings within the refrigerant lines, it sticks to the actual rotor, and when it spins, it will actually scrape and nick the actual stator which is what leads to those turn-to-turns. So the likelihood of them both wearing out at the same point is like 1 in a million. However, the likelihood of them getting hit with a piece of metal at a high rate of speed and cutting them both at the same spot is extremely likely, and that's most likely what caused your grounded compressor. This compressor lived for a year, right?
Yeah, it wasn't a factory. It would have done it immediately.
Oil looked great, except for a few particles in the base of the actual compressor. And when we pulled the stator, you found that, or pulled the rotor out of the stator, you found that there was actually metal shavings underneath that cover plate around the side. And how would you know, right? Did it die from overheat? What did the oil look like? We wouldn't know unless we tore the compressor down to find the problems.
It's absolutely crazy.
It is. And so the world of compressors, the world of compressor oil, you wouldn't think that we could spend 50 minutes talking about it, but we could probably actually spend a lot more time.
I could go on for hours. This is a really cool topic.
A lot of pressure on it.
Well, and that's the thing, too, is that you don't know what you don't know. And there's a lot of areas of concern. There's a lot of areas that you should be testing. Not just when one of my favorite things to do is when you pull an old compressor out of a system, you weigh the old compressor compared to the new compressor weight. The difference in weight is actually oil. And so with that difference in oil lets you know, is there an extra 16 ounces in the system? Is there 16 ounces less in the system? What that amount of oil weight difference will tell you, do I have an oil return problem? Do I have trapping in the system? Is there, refrigerant charge discrepancies that I should look at? Because if that compressor is double oil charged out of the old unit, right? You're like, wait a minute, then that means the compressor next to it has no oil. And now I should be really concerned. Because if I put it in there thinking I'm just going to go down the road, that small amount of just measurement between the two, it can be a huge problem, right? Because now you've just removed, again, 36 ounces of oil is what I've actually seen, which is insane because, again, that's a lot.
I got a better one for you. We cut out a compressor and it had 0 oil in it. We went 10 feet down the line and found 2 gallons.
Whoa.
Yeah.
That's crazy. Was it trapped? What was the problem?
So
you can't just toss that out there or not.
It went from a 4-story roof down underground and then back up 2 stories.
So giant trap.
Gigantic trap.
See, and so again, and that's a whole conversation itself, traps. But it's one of those things where, as long as you follow manufacturer's best guidelines, and I know that's a really big gray area for traps, as long as you do the best you can with what you have. Again, with 410A systems, we minimize traps. With mineral oil, we were trapping like crazy, right? You couldn't go more than 5 feet without doing a trap, sometimes a double trap. And so with that being said, especially in vertical risers, with 410A, the miscibility with POE and also PVE is extremely high, and so we get rid of those traps. So when you go to VRF, especially when you have a compressor that can overclock and ramp up way above what a normal compressor might run at speed-wise to get that velocity and that volume of refrigerant flowing, traps are not needed. If anything, you trapping or thinking that the old trapping rules follow causes only more problems. The system has a way to overcome, issues and elevation changes. Don't trap on purpose, and don't go out of your way to make a trap to make something look beautiful.
Right, we're trying to build pressure, and trapping sometimes can reduce the pressure that we need.
Build pressure on one side.
Yeah,
right.
Not so much the other side.
Yeah.
Right. It's that whole laminar flow and turbulent flow, right? We want to, every 90 that you hit and you go through, it adds a certain amount of length for that actual copper line set, and so we want to avoid that at all costs.
Well, gentlemen, this has been really, really fun topic to talk about. We're 53 minutes in. I don't want to take up too much more time, your time today, but this has been a really cool topic, and I really am looking forward to this video.
Yeah, no, so we're going to probably release 2 different versions of it, maybe a small clipped up one that's really easy to digest and flow through, and the other one will actually be probably like an hour of us just talking about things.
I'll take the nerdy one.
Just because you get caught up in conversation when you're actually doing something. And let's be honest, heating these compressors up happened really fast, but cooling them down took a while. So, yeah. And thank you for Ty for actually hopping on here with us. And
thank you very much for jumping in as our first official guest on the VRF Tech Talk podcast.
First official guest, yeah. I'll have to give you a sticker or something. We don't have those, but we'll have to get some now.
Some checker stickers.
There we go. I definitely gave him those, so. All right, so I guess until next time, if you guys want to know more about oil, compressor cleanup, we have the VRF Tech Talk Facebook page. There's a lot of documents that are on there. Feel free to always reach out to myself or Donald, and I would say even Ty is willing to take on conversations. He's always out there helping people. The knowledge is out there. Start asking the questions. Don't guess. Test. And if you have anything else that you guys want to
Just
talk about,
test.
or yeah,
God, that's a great line. Oh my
Did you
goodness.
just come up with that? 'Cause
I did
that is,
actually. Yeah,
That is
that's gonna have to be a,
great. Oh my
that's better
goodness.
than if you're not testing or guessing. Like that's just simplified. Yeah, that's got to be a bumper sticker. I need stickers with that.
that's
That was
No, I'm just kidding. But to that point, just know that we're all here. We're not we're not hidden behind secret walls here, right? We're
we
here
don't
to answer
gatekeep it.
questions and information. We're always available. Reach out to us. That information is out there. It may be closely guarded by manufacturers, but a lot of us here have worked for manufacturers and know where to find it. Don't make excuses. Let's be a part of the solution, not the problem. I think those
Absolutely.
are all the catchphrases that I have so far.
That's great. All right, guys. Thank you so much.
All right, talk to you later, man.
Bye.
Bye.